Hi, this is a walkthrough video for the energy skate park simulation. If you haven't done this lab worksheet, make sure you go and follow the instruction and try it yourself first. So let me go now and set up the simulation. You can open the simulation with the link that I provide to you and go to click the second tab, change to this track, and that's basically it. For the first investigation, we'll have to study the gravity against the final speed. So first of all, we'll have to put the skater, because we don't want it to slide always, so we should pause it and then put her on top. And then if we just don't change anything, and we should find the final speed should be about 10.8 something. So here I got 10.82, which is something you can fill in right here. So 10.82, and then we'll have to change the gravitational acceleration. That means the gravity in the simulation. So the next one, let's go back to 6. Okay, and then we'll do the same thing again. And that's 8.47. And then we'll go for 2. And just try again. And you can also witness that it takes longer time. Okay, so 4.89. And then go for 14, which is the other way around. Much quicker, obviously. 12.93. And then for 18, 14.66. 22, 16.21, and then 26, 17.62. So notice that because your initial position may not be exactly the same as mine, so it might happen to you that maybe your last digit, your second decimal place, will be different from mine. But I think for the first decimal place, you should be the same. Or if you round up, it should be the same. So you can take my data as reference for yours. And so the next thing that you need to do is to plot a graph using either the Microsoft Excel or the Google spreadsheet. And in case you don't have Excel, I guess I'll demonstrate how you can do it with Google spreadsheet. You just have to copy this to the Google spreadsheet, let's say like this, and then you have to highlight this whole table and then click insert chart, and by default I think they would choose a scatter graph for you. Okay, and in case they don't, you can still change it here. Don't use the line graph because that's not useful in physics. That doesn't reflect the trend. So use a dot, but then there's no line of best fit you can see. And so what you have to do is to click it, and then on the right hand side you'll be able to see trend line. So click this and you see a straight line, and obviously you see that the relationship between what we are finding, the gravitational acceleration and the final speed, they are not linear, obviously. Okay, I hope this is something that you can judge based on the numbers itself. And so obviously we have to change the type of the mathematical relationship, and by trial and error, I guess you may find the best one should be power series. You may say that polynomial is close, but in fact later on you understand using power series is the one that is relevant to the physics idea also. So using this, you can see the line really pass through all the points. The most important thing is you also need to show the equation itself, because that's what I asked you in the worksheet. And so what you have to do is to click this one. No, not this one, sorry. This one, label, and use equation. And so here you can obtain the equation. And I actually don't like how they display. Here it actually means y equals to 3.46 times x square root, basically. But then I don't think I can edit it or give it more decimal place, because this is not exactly 0.5. when I try on Excel, I can show you now. So this is how it looks like on Microsoft Excel using similar steps. The most important thing is when I set this as in power series, that means the power function mathematically, then I would get this equation, and you can see that the index for x would be 0.4997. So I feel this is more realistic to you other than 0.5 instead, because that looks quite artificial. So either way, you can use this as a screen capture, and then you can just paste it on your lab worksheet. Here we go. And the next question you can see is asking you using the physics formula in this chapter, so probably more than one. Derive the equation of the line of best fit in your graph. So remember, this is something that we did from the data, from the experiment itself, but then we can explain it using the formula that we learned earlier in this chapter. So if you look at this, again, this equal to y, and if you look at what y and x will represent, basically it means 3.46 times the x, which is g, square root equals to v. So something like this, right, we want to see. And so think about the physics formula that you can describe in this system. If you haven't done that, I will allow you to pause the video and try first.
A few moments later.
Alright, so the relevant formula is simply based on conservation of energy. And thinking about at the very beginning, what you have is GPE here, and then eventually it will all convert it into KE. So you can say GPE at the beginning equals to the kinetic energy at the end when you are leaving the track. So for GPE, you can recall the equation is mgh. For KE, the equation is half mv squared. And then by deriving further, we can see that the m will be cancelled out, and then you can try to rearrange it so that it looks similar. So you should get 2g, actually I'll put h first, and then times g equals to v squared, and now it gets closer to what we are trying to make. Eventually, we have v equals to root 2h, and then root g as well. And this is the reason why I choose the power series for the line of best fit when I plot the graph, because you can see it match very well. If you use other one, let's say you may find again polynomial look also pretty good. It's also a curve that kind of pass through all the points. But then if you look at the formula, you can see that 3.5, which is a constant, plus 0.8x plus a negative 0.01x squared. So it doesn't make sense at all, right? If you compare with the so-called physics framework that we have based on the fundamental formula that we find in the earlier video.
Here comes a new challenger!
Let me also introduce you a secret Easter egg here. So as you can compare, v is here and then root g is here. Then think about this. Why is this equation must giving you 3.46 in our data? Why not other numbers? Let's pause the video and think about it.
A few moments later.
Alright, so the answer is that if you try to compare 3.46 with the formula that we derived, it actually corresponds to the constant root 2h. So if you try to put them together, and if you try to resolve it to find out h, so what you have to do is 3.46 square and then divided by 2. And according to my data, you can try with yours as well. Again, your equation may be different from mine, but I guess your answer should be very close to 6 meter. And 6 meter is basically what we have here. Alright, your initial height will be 6 meter. So it's not a coincidence, it is meant to be like that.
Oh my god! Wow!
part 2, study the mass against the final speed. So without resetting, simply change the gravity back to 10, because that is mimicking the Earth, and then change the mass according to table 2. So without changing, it would be 60, and it should give you around 10.9. So let's try. Okay, and yes, 10.93. So maybe I can, well, if you like, you can change it to 3 here. And then the other thing simply you have to do is to change the mass accordingly. So let's start with 20. Okay, and you'll find 10.93, and in fact, since you have done it, I suppose you should find this one is always 10.93. So yeah, I actually don't bother to try. So all these are the same. And of course, that's why I didn't ask you to plot the graph in the next part. And so the relationship that you could observe is actually no relationship. I mean, having no relationship is also a kind of relationship. Alright, sorry, maybe I have reminded you something sad in your life. Let's move on with physics. Physics is always true to you, and it will never betray you. So number 5 asks you how to explain using the relevant formula. So in fact, it's the same sort of formula that you have earlier. So GPE equals to KE, because we are also doing the same kind of motion. So mgh equals to half mv squared. And you can say that, hey, because of this, we can see that m are cancelled out. So mass is cancelled out on both sides of the equations, and so it will not be affecting anything else. It's not going to affect the v or anything else. And so that also means no matter what mass it is, as long as there is an object that changes GPE to KE, assuming there's no friction or air resistance, then the velocity will always be the same. This coincide with what we have mentioned in the previous chapter when we talk about the Tower of Pisa, the experiment that done by Galileo, dropping two heavy mass. One of them is heavier than the other, and eventually he find out the final velocity, or the time that it takes to reach the ground, is the same, disregard of the mass. So coincide with what we have here from the energy perspective. Okay, moving on, we will study how friction affects the final speed also. So let's set by default as control variable, gravity will be 10 and mass as 60 respectively. So okay, back to 60. And again, we will just have to repeat a few trials. And this time, because for the friction, there is no set value that you can choose from. It's more like a scale that you can kind of choose from a continuous scale. So I try to make it easier for you to select. So let's do none, a quarter, half, 3/4, and full bar. So let me try it now. So with none, I guess it's the same as what we had earlier. So 10.93. And then with about a quarter, again, your answer may be different from mine, simply because it is a bit, I think this is, okay, this one is better to be a quarter. And so it should be something like 10.23. Okay, so 10.23. And then for about in the middle, we would get 9.95. 9.95. And then 3/4, we get 9.47. And then finally, full bar, we will get even slower, of course. So 8.76. 8.76. And so the qualitative observation is very obvious that when friction increase, then the final speed would decrease. That's the qualitative observation. And so here again, try to build and write down the relevant formula to explain how come when we increase the friction while keeping the others variable the same, the final velocity will be lower. Of course, using the energy equations that you learned. So try it out if you haven't.
A few moments later.
Alright, so think about this. Again, at the very beginning, you have the only energy as gravitational potential energy. And then when you are leaving the track, not only this time you have KE, part of the GPE has converted as work done against friction, because that would take away your energy simply, right? And of course, if you're asking, oh, where does that go eventually? That would turn into thermal. So that's why if you try to pay attention to the simulation, the thermal energy would increase. So right here, yes, you can see, oops, it's gone. So maybe I'll try again. Okay, with the friction setting, you can see now about 1,200 joule of thermal energy was, turned from the potential. So that's the reason behind. And so if you really want to explain using the formula, then we should write this: GPE will equal, because of energy conservation, KE plus the work done against friction. And so mgh equals to half mv squared plus friction. Work done equation is force times the distance. And so the distance that we are referring to here will be the one that is going along the track, of course, because this is where the friction is provided. And so we don't have the actual number, but then we can see from the relationship of this equation that since m doesn't change, g doesn't change, h doesn't change, and also d doesn't change. Again, d is the length of the track itself. We didn't change in this investigation. And so leaving you with only v squared and f to be the one that could vary. And so since we increase the friction along the different trials, then what happened is, since everything else is fixed, then the only way you can change v would then be smaller, because you can see this is on the same side, on right hand side, and mgh is fixed on the left hand side. So the only way that you can do, like what we said, is v square being smaller. So try to turn my symbols here into a sensible sentence by yourself. Lastly, let's try to study the height against the final speed. So this time, since it's kind of messy, so let's just reset and try to pick this track again. And I will want you to enable the grid view. By dragging the red dots, you can actually change the initial height. And so we can do 8, 7, 6, 5, and 4, and I think that may be good enough. And again, notice that you shouldn't be dropping it, because what happens is you then can get more energy for the skater, and that's not what we want to study. Alright, we want to see how initially the height will affect the final speed only. And so let's start with 8 meter, and we should find 12.48. So let's go and type here 12.48, and then repeat the same for the others. So maybe we have to adjust like this. Notice that you should do the center of the red dots. Okay, and let's try again. So this time we got 11.66. Okay, 11.66. Okay, next up for 6 meter, 10.73. So 10.73. Okay, and then we can go for 5 meter. Okay, we locate it. we got 9.75. And lastly, 4 meter. And by the way, it doesn't really matter where you put here, here, or there. I think this is just more like realistic. I mean, it shouldn't affect, since this is a simulation, so it shouldn't affect which position. As long as it's on the same horizontal level, that will be fine. So lastly, we got 8.59. And if you think about it, the whole motion is still the same as what we have previously. That is simply GPE all turning into KE. There's no work done because we have excluded friction in this investigation. So for your formula, you also start with GPE equals to KE because that's what happened. And again, that's mgh and half mv squared. Cancelling out the m first, and then you can try to compare with what we get. So we try to get h to be here, and probably we will have the 2 moving on one side because you want to keep the v on here. So 2gh equals to v squared, and so we have to square root it, obviously, v root 2gh. So I guessed. And so similarly, you are going to copy these to plot the graph like how you did for investigation 1. And again, you can try to add the line of best fit. It looks like passing through all the line, but again, if you try to use linear line, it won't work later on because that's not is how it's meant to be using the energy equations framework. So again, you should use the power series, and that should give you the equation like this one, 4 times x to the power of around 0.5. So here you go, and again, notice that it should equal to y, and that means 4.08 x, that means height. And then here you can take this as 0.5 simply, and that is having the square root here, and y is going to be v. And so this is something that we are aiming to get into the shape. So for the next part, again, it's the same as previous. You simply have your GPE initially turn into KE, and again, there's no work done, so you don't have to consider plus anything. Just 100% of GPE turning into KE. Stating the equation, mgh half mv squared. And first of all, cancel the m first, obviously. And then you'll be able to get the 2 on this side. 2gh equal to v squared, and you can see we want to keep it as v only, right? So we should take the square roots on both sides, and you eventually get 2g and also the root h as well. And so this would match with what we get from the line of best fit in the simulation data, and also explain the relationship between v and h. You can say either v proportional to root h or v squared proportional to h. Both are the same. And also you can notice one more thing, just like previously, there's a reason for why it is 4.08, and that is because it corresponds with the term, the coefficient you may call root 2g. And if you try to calculate the g by equating them, you should be able to find out the one that is close to the one that we set in the simulation. So 4.08 squared divided by 2, we would get 8.3. And you may say, hey, Mr. Wong, this is actually quite far away from the actual expected gravity, 9.8. I put a thought to it, and I think other than the fact that when I set up say 4 meter or 6 or 7 meter, I could not make it exact at that position. But other than that, I think another reason is simply the data doesn't really follow through the power equation that we expect to be in the power of 0.5. Notice that this is 0.538, so that actually affects the coefficient itself. If we can somehow force it to be 0.5 and changing the coefficient at front, then it should work. But then I think that is beyond what we want you to learn in IGCSE already. So I feel let's just keep it for now, alright? So 8.3. And if you're interested to know how we can do it with another approach so that we can get this number more precisely, study IB Physics. So that is all for this video. If you enjoyed it, please hit the like button and subscribe to my channel. I'll see you again in the next video. Bye.